Welcome to the deep dive. We take stacks of sources, information, and really try to pull out the key insights for you.
That's the goal.
And we're continuing our series on the Online Encyclopedia of Integer Sequences, the OEIS, really aimed at you number theory students listening in.
A fantastic resource.
Absolutely. So today we're focusing our mathematical detective work on one sequence, OEIS A000274.
Good one.
The main description is number of permutations of length n with two consecutive ascending pairs.
Right.
So the sequence starts out 0, 0, 1, 3, 18, 110, keeps going. Okay, let's maybe unpack that definition first. Number of permutations of length n with two consecutive ascending pairs. It sounds clear enough, but what does it actually mean in practice? And, how do we get those first few terms? Like, where does that 1 come from for n3?
Okay, yeah, good question. So for n1 or nd2, you can't possibly have two consecutive ascending pairs. There aren't enough elements. So those terms have to be 0.
Right, makes sense.
But then you get to n3. You look at all the ways to arrange 1, 2, 3. 1, 2, 3, 1, 3, 2, 2, and so on. And only one of them, 1, 2, 3, actually fits. You've got the pair 1, 2, which is ascending.
Yep.
And you've got the pair 2, 3, also ascending. And critically, they're right next to each other. They're consecutive.
Ah, okay. So only one permutation works for n3. That gives us the 1.
Exactly. That's the core idea. But, and this is where it gets really interesting, Emmerich Deutsch found this completely different way to define the same sequence.
Oh, another definition for the same numbers.
Yes. He showed that AN, our sequence term, is also the total count of what are called exceedances across all the derangements of the numbers 1 up to n1.
Okay, hang on. Exceedances and derangements. Let's clarify those.
Sure. A derangement is just a permutation where absolutely no element is in its original position. Think of shuffling letters in envelopes, and none end up in the correctly addressed envelope.
Got it. Nothing stays put.
Precisely. And an exceedance. That's simply a position I in your permutation, let's call it P, where the number in that position, Pi, is actually greater than the position number itself.
So position 3 had the number 5. That's an exceedance.
That's an exceedance at position 3. Correct.
Wow. So you're telling me counting these exceedances in these special permutations, the derangements of n1 items gives the same number as counting permutations of n items with two consecutive ascending pairs.
Exactly the same number. It's quite remarkable. The OEIS entry gives the example A5 equals 18. And that 18 comes from counting up all the exceedances you find when you list out all the derangements of 1, 2, 3, 4.
That feels, well, almost magical. Finding these hidden connections between seemingly unrelated counting problems.
Yeah.
Does that happen often?
It's one of the beautiful surprises in combinatorics, yeah. It suggests there's some deeper mathematical structure linking these ideas, even if it's not obvious at first glance. It's not just a coincidence.
Yeah. Right. So, okay, we understand what the sequence counts, maybe even in two different ways. Yeah. But how do we actually, generate more terms? Especially without listing everything out, which gets impossible fast. This is where the OEIS formulas usually come in, right?
Absolutely. And AN00274 has some really interesting ones. There's a core recurrence relation, which is often very useful.
Right.
It looks like this. AN 1 plus n, AN1 plus 3 plus n, AN2 plus 3n, AN3 plus 2n, AN4.
Whoa. Okay, that's quite something. You need the 4 previous terms to get the next one.
Yeah, it's a 4-term recurrence. It shows a certain complexity, but it means if you know the first few terms, you can compute any later term systematically.
That complexity, needing 4 terms, does that itself tell us something deeper about the sequence?
It often hints at intricate dependencies as n increases. But there are other ways to capture the sequence, too. There's also an exponential generating function, an EGF.
Yes, the EGF. A sort of compressed formula for the whole sequence.
Exactly. It's like packing the entire infinite sequence into a single function using power series. For this sequence, it's by 22 xpx, 1 by 2. Generating functions are incredibly powerful tools in combinatorics and analysis.
Allows you to use calculus tools on discrete sequences, sort of.
Precisely. And then there's this other formula listed as conjectured, which is really fascinating.
Conjectured, meaning we think it's true, but maybe no solid proof yet.
Often, yeah. Or the proof might be complex or unpublished. This one involves factorials and, surprisingly, the number e.
Euler's number. In a counting problem.
Right. It's AN12, NAN1E. The square brackets often mean rounding to the nearest integer, or sometimes the floor function, depending on context, but seeing e there.
That is weird. It usually shows up in continuous growth calculus.
Exactly. Finding it in a discrete combinatorial setting like this is always a bit mind-bending. It suggests connections between continuous and discrete math that are, well, profound.
Are there any simpler-looking formulas?
Well, there's a really neat one using Mathematica notation that ties things back beautifully. It says you can get the terms using table subfactorial nn2, n2, 20.
Subfactorial and, what's that?
Ah, that subfactorial is just another name for the number of derangements of n items, sometimes written n or dn.
Oh, so that formula directly uses the number of derangements we talked about earlier.
Exactly. It explicitly shows that deep connection. The number of permutations with two consecutive ascending pairs is directly related, via this simple formula, to the number of ways to derange things. It connects Deutsch's alternative definition right back.
Okay, that ties it together nicely. So we have the definitions, the formulas. What about its place within the OEIS universe? Is it like a famous sequence connected to others?
Oh, definitely well connected. The OEIS page lists loads of cross-references. Things like A01000007, A0000000166, A00000313, A00012660, A001261, and several others.
So it's related to many other sequences people study.
Yeah, each reference is like a potential link. Maybe it's a special case of another sequence or part of a formula for a different one. It shows how these sequences form this huge interconnected web. It's even mentioned as being a diagonal in a related number triangle, A01000007.
Interesting. Any other identifiers? Keywords?
Yeah, the keywords listed are non and easy. Non just means non-negative terms, which is obvious here.
Right.
But easy. Well, given that four-term recurrence in the formula with E, maybe easy is a bit relative.
Hey, yeah, perhaps easy for the OEIS editors, not necessarily for us working it out by hand.
Quite possibly. But it also shows this isn't some obscure new sequence. It has history. It's mentioned in Sloane's own books from 73 and 95.
Ah, the founder of OEIS.
And it goes back even further. Work by F.N. David, M.G. Kendall, D.E. Barton in 1966, and John Riordan's classic combinatorics book from 1958.
Wow, so it's been studied for a long time.
Definitely. Plus, there are online links. Eloise Hines has tables. There's a key paper by Mantassi and Rakotandrajau that Deutsch actually cited, titled Exceedingly Deranging. Apt title, right?
Perfect title. So, a sequence with quite a pedigree.
For sure. It's clearly established and relevant in combinatorial analysis.
Okay, so we've taken quite a journey with 00000274. We started with its seemingly straightforward definition about ascending pairs.
Right.
Then discovered this surprising link to derangements and exceedances. We looked at some pretty powerful, if complex, formulas.
The recurrence, the EGF, the E formula.
And finally saw how it fits into the bigger picture of the OEIS, connecting to lots of other sequences and having a solid history.
And a nice little exploration.
Hopefully it encourages you listening to keep digging into the OEIS yourself. It's just packed with these kinds of connections.
Absolutely endless discoveries to be made.
So for a final thought today, just consider how these completely different mathematical ideas, counting permutations with a specific pattern and counting exceedances in derangements, somehow ended up describing the exact same sequence of numbers. What might that tell us about, the deeper underlying unity or structure within mathematics itself? Something to ponder.